Hi, everyone, and thank you for joining us today for our webinar, Mitigating Corrosion, a Two-Pronged Approach. My name is Kim Melton, and I will be the moderator for today's presentation. But before we dive into introductions, I would like to go over a few logistics. First and foremost, if you have any questions throughout this presentation, you can submit them at any point in time, and we'll address them at the end of the webinar. Now, if you don't see any a Q&A feature to the right side of your screen right here, you'll need to click the little circles across the bottom. There's one with an ellipsis in it, and when you click that circle, it'll open up a menu with Q&A at the top. All you have to do is click that Q&A, and it'll open the feature on the right side of your screen that you can use to submit questions, and we will answer all of the questions at the end of the broadcast. Now, a quick note before we get started, this webinar is for educational purposes only and should not be used as a substitute for professional engineering design, consultation, or documentation that may be required by building codes, contracts, or even applicable law. So if you have any questions after this webinar, you can refer to our specific application guidelines and instructions, and those are located in the product sections of our website. Additionally, we'll follow the webinar today with a survey, and this is your opportunity to provide us with feedback on how we did. You can even use it to ask additional questions that you may think of after the webinar has ended, or suggest new topics for future webinars that you'd like to hear. Now, this is all part of how we deliver the JAME experience to you, and the JAME experience is based on 4 pillars of our cultures, and you can see those listed there in the bottom left corner, and that's people, passion, perform, and protect. Now, it's critical for us to make sure that we're hearing feedback from our audience and listening to how you guys are receiving our content. So we offer surveys like this one to help make sure we're delivering the JAME experience to you and make sure that our content is robust and educational like we want it to be. But this is a two-way street, so we need to hear your feedback on that. So with that, I will turn it over for introductions and kick us off with Chad Meyer.
Thank you. My name is Chad Meyer. I'm the Midwest and Northeast Regional Sales Manager. I started with JM in 2006 on the mechanical pipe and equipment and air handling side of the business. And I've been doing industrial for the last 6 years.
RT Boehm, Business Development Manager, located in Kansas City. Territory responsibility covering the Midwest and the Northeast. I came over to Johns Manville in December of 2019, part of the ITW Insulation Systems acquisition. Previously worked for ITW for the past 30 years.
Good afternoon, everyone. I'm Scott Sinclair. I'm the Regional Technical Manager for the Eastern and Midwest U.S. and Eastern Canada. I've been with Johns Manville since June of 2019. Even though I am actually a degreed electrical engineer, I've been working in the industrial insulation industry for the last 15 years. So let's get started and take a look at what we're going to cover for you today. We're going to start taking a look at corrosion under insulation, or CUI, and do a brief overview of what it is, how it happens, and what the impact is to industrial facilities and the global economies. Then we're going to look at different aspects of corrosion under insulation and consider the impact that jacketing can have on helping to inhibit corrosion, the influence of insulation chemistry on corrosion, and the impact that hydrophobic or water-resistant insulation products can have. And then we'll follow that overview with some detailed information on different testing that has been performed to evaluate the direct impact of different insulation materials on corrosion under insulation. So let's get started and take a quick look at corrosion under insulation. In 2013, NACE, which is the National Association of Corrosion Engineers, did a global study called the Impact Study to try and take a look at assessing the cost impact of corrosion. And they concluded from the results of their study that the global economic impact was about $2.5 trillion. Additional studies have been done looking more specifically at the impact of corrosion on corporate spending for maintenance budgets, and have shown that in the oil and gas industry in particular, about 40 to 60% of maintenance budgets are typically allocated toward addressing the impact of corrosion under insulation. So you can see that the financial impact is quite significant. If you break that global information down into a bit more detail, you can see this is more of the data from the NACE impact study, broken down by different geographic regions and across different market segments in the economy in those regions. And if you look at the box that is highlighted or outlined in the yellow or pale orange, you can see that the impact to the industrial sector within the U.S. alone was about $303 billion. And remember, this was 7 years ago that this study was published, so that impact will obviously be quite a bit higher by now. And then if you move further over to the right on that same row for the U.S., you can see that the total cost of corrosion in the U.S. was about 3 times that, or $451 billion, or almost 3% of our gross domestic product. On a global basis, that $2.5 trillion figure represents about a 3.4% impact on gross global product. So again, reiterating that the impact, financial impact of corrosion is very, very severe. For corrosion to occur, you actually need a combination of conditions to be present. Those conditions are the presence of oxygen, the presence of liquid water. While water vapor itself will not create corrosion, it doesn't take much for the water vapor that gets into an insulation system to turn into the liquid form. So if you do have significant water vapor ingress in your system, you do have the potential for corrosion to occur anyway, because it's very likely that it will turn into liquid water. You do need a corrosive environment, and that can be either corrosives entering the insulation system from the outside environment, or potentially corrosive compounds or materials being leached out of the insulation system itself. And you need that to be acidic or to have a pH of something less than 7. And then the system needs to be operating in what is referred to as the corrosion zone, and that is typically considered to be that temperature band between 100 and 350 degrees Fahrenheit. So if you take a look at that, you can see that there are a combination of conditions that need to be present, and some environments will introduce those conditions to a higher or lesser degree than others, and therefore have a significant impact on the exposure of the system to the opportunity for corrosion to occur, and also impact the type of corrosion that happens and the rate at which that corrosion happens. And now Chad will talk a little bit about the different types of corrosion that we can have.
And there are several different types of corrosion that we can see. We can see 2 dissimilar metals in the environment causing corrosion to each other. We can have salt water on direct contact with steel. You can have salt water just in the open air over time corroding the steel. You have simple rust on steel, or the materials in the environment over time will cause corrosion. But what we want to focus on today is more of the pitting or crevice corrosion that can occur. What is pitting corrosion? Pitting corrosion is a more localized form of corrosion. This can form holes or pits in the metal. This occurs when one area becomes anodic compared to the other areas around it. And this can lead to a failure with minimal overall metal loss. So if we look at what we call the corrosion temperature bandwidth, what we're looking here is kind of a graphical representation of all of the products that are used on hot systems today. And we would consider this what we call high risk. So this is going to be a system that would be ambient up to 350 degrees. And when you have something operating in this, you want to pay close attention to what's going on with the system, because you're at a pretty high risk of developing corrosion under insulation. The other area we want to talk about is a cyclical system. So it's going to be a system that is going to cycle between hot and cold, anywhere from below 0 up to 600 degrees. Could be a simple steam system that for half of the year is running steam distribution and the other half of the year is running ambient. But this is what we would call more of your critical system for CUI. So if you have something that's going to be cyclical, you want to definitely pay a little bit more attention to a system like this for CUI concerns. So how can we inhibit or prevent CUI? You know, some people would say that we really can't prevent it. All we can do is slow it down. So we're going to take a few minutes today to talk about how the insulation itself, the chemistry, can impact CUI, and how the metal jacket can be your first line of defense.
Hello, this is R.T. Boehm, and I will be discussing the metal portion of the webinar as it pertains to CUI. There are 3 important aspects of metal jacketing and how they relate to reducing the amount of corrosion that can occur. In this section is the classic CUI on pipe, tank, and equipment, but also corrosion to the metal jacketing itself. The 3 primary aspects are metal types and alloys, the value of using polyfilm moisture barrier on the inside interior of the metal jacketing, and the critical importance of a proper installation. In North America, there are 2 types of metals, various alloys, and some coated metals used in the mechanical insulation industry. From the top to the bottom of the table, metal jacketing materials are shown in order of increasing resistance to corrosion, but also note as the material becomes more resistant to corrosion, they also become more expensive. There is not a single best jacketing material. There's just a lot of factors to be considered by the project engineer, including corrosion resistance, cost, and other factors not discussed in today's webinar, but also the weight, the strength, and the fire resistance. Aluminum jacketing comes in 2 interchangeable alloys, 3003 and 3105. Aluminum is the most commonly used metal jacketing in North America. Its performance, including corrosion resistance, is adequate for most projects. Painted aluminum offers better corrosion resistance than bare aluminum, and it also has a lower emittance, which can be important to some applications. The next step in corrosion resistance and cost is type 304 stainless steel. This is used where the ambient environment provides an increased but not a huge risk of corrosion. An example might be a facility near or not directly on a seashore. Next, typically type 316 stainless steel might be used in a particularly harsh outdoor climate, such as offshore or directly on the seashore. Finally, the most expensive is the stainless steel metal jacketing with either Kevlar film or Kynar paint, rarely used although very effective in the harshest environments. Next, we will discuss the value of polyfilm moisture barrier, or PFMB. PFMB is a 76 micron or 3 mil thick plastic heat laminated to the interior of the metal jacketing. This is not a proprietary product and is also available from all jacketing companies. The purpose of the PFMB is to inhibit corrosion on the interior surface of the metal jacketing by preventing moisture from contacting the inner surface. Basically, it's a plastic barrier on the interior of the metal jacketing. PFMB will minimize pitting and crevice corrosion of the jacketing on hot and cold systems, but also minimize galvanic corrosion to pipe or tank on hot application where there is not a vapor retarder on top of the insulation. PFMB offers superior performance over the 2 older outdated technologies used, known as polycraft or painted barriers. PFMB is not a vapor retarder. A vapor retarder goes on the outside of the insulation to reduce the entry of water vapor into the insulation system. PFMB goes on the inside of the metal jacketing, and its purpose is to reduce the likelihood of certain types of corrosion. Now we will discuss the value of metal jacketing and its importance of a proper installation. A well-jacketed system is the first line of defense to preventing water ingress. There are many important aspects to metal jacketing installation to help minimize moisture entry into the insulation system. First, ensure there's a 2-inch overlap on both the longitudinal and circumferential joints. Next, ensure joints are orientated naturally to shed water and face away from prevailing winds. We have previously discussed the value of PFMB, and also ensure jacketing strength and thicknesses are adequate to resist mechanical abuse and environmental conditions like acid rain, high humidity, on and off seashore locations. Metal jacketing is typically 36-inch wide and is sized to fit around the insulation while leaving a 2-inch overlap. The longitudinal overlap is positioned to naturally shed water from or face away from prevailing winds. The circumferential or butt joint is at either end of the metal jacketing and also requires a 2-inch overlap. This joint as well should be orientated to naturally shed water or face away from prevailing winds. Depending on the type of system, hot or cold, the jacketing will require either screws or rivets or banding with wing seals. It is important on cold systems never to use screws or rivets, as these products will pierce the vapor retarder. A sealant or silicone can be applied to the metal jacketing, although this is controversial. Whether to seal metal jacketing is a controversial topic and is up to the individual specifier. There are many pros and cons to this topic, and it has not been studied scientifically. On the pro side, sealing will prevent water from entering into the insulation system, which certainly makes sense. On the con side, water is able to exit from improper installation or seams. This is especially important on hot system where the pipe and tank is high in temperature and the potential for water ingress forms from the insulation material is much greater than in cold applications. Also, sealing will cost more money and time. There's also a concern of the system's expansion and contraction. This will damage the seal and can result in a waste of time and money. Ultimately, it's up to the individual specifier to seal or not to seal. If a sealant is used, it is critical that the seal the inside of the joint and not the external lip. Most sealants are not UV stable and cannot be exposed to the sunlight. We have discussed the proper material selection, system design, and installation of metal jacketing are important to the success of the system's performance of the insulation system. The main function is to inhibit water intrusion, and if there is no water that enters into the system, then there can not be CUI. However, if metal jacketing is damaged, not installed properly, or sealant failure, additional lines of defense against CUI are necessary. Metal jacketing can reduce intrusion, however, water is inevitable. So you need a backup plan or additional lines of defense against CUI. Items to consider: coatings, pipe and tank with corrosion inhibiting coatings or gels, proper system maintenance, choosing proper insulation materials such as hydrophobic or XO additives that help inhibit CUI. This brings us to the next section with Scott Sinclair to discuss combating corrosion and insulation materials.
Thanks, RT, for an excellent overview of the impact that the metal jacketing system can have on corrosion under insulation. And as RT said, I'll now talk a little bit about the impact that the insulation material itself can have on CUI. One of the primary features that many insulation manufacturers are offering these days to help combat the opportunity for corrosion under insulation to occur is by making their materials hydrophobic or water resistant, water repellent. Hydrophobic insulations are designed to help prevent water intrusion. There are many different insulation material options available that do offer this feature, and most are designed such as they allow water vapor to still pass through the system, even though they will repel liquid water. To do a quick overview of some of the options available for hydrophobic or water repellent insulation materials, the Johns Manville Minwool 1200 pipe insulation is a water repellent or water resistant product, as is the Thermo 1200 calcium silicate. The Insulthin HT and Spool WR 1200 perlite are both hydrophobic products. In addition, most of the silica aerogel products that are available are considered hydrophobic, as well as cellular glass insulation, very often used in ambient and below applications, where cellular glass is considered to be a zero perm material. However, you do need to pay very specific consideration to the seams, as the seams and joints obviously will not be impermeable to moisture and water. But you do have to pay attention to one very critical aspect of the features of hydrophobicity and water repellency, in that most materials get this capability by the addition of a treatment, usually an organic silicon, in the insulation material during the manufacturing process. Most of those treatments, as I mentioned, are organic in nature and therefore will oxidize or burn off at temperatures between 300 and 500 degrees Fahrenheit. Once the material has been exposed to those temperatures for any significant amount of time and that organic treatment has burned off, water will then be able to penetrate and saturate the insulation material and come in contact with the pipe surface, thereby contributing to the opportunity for corrosion to occur. Once that material loses its hydrophobicity, insulation chemistry now becomes a much more critical factor in looking at how the material can impact CUI and help try to prevent or delay the occurrence of corrosion under insulation. The ability of the insulation chemistry to impact corrosion under insulation has been demonstrated through two different test methods that have been developed. The first is the ASTM C1617 standard and test protocol, and the second is a newer long-term test protocol that's being developed to be more indicative or replicate real-world conditions, but under an accelerated corrosion timeline. And we'll review information for both of these today. Let's start with the ASTM C1617 test protocol. One of the big advantages of this as compared to some prior test protocols is that it was designed specifically to look at corrosion on carbon steel, whereas many of the prior standards were focused on stainless steel. The procedure for performing this test is to take the insulation material, grind it into a powder, or shred it as finely as you can, mix it with DI water, blend it together, then filter out the remaining solids so that all you have left is the liquid with any compounds or materials that may have leached out of the insulation itself that could contribute to corrosion. That liquid is then dripped onto the surface of the coupon. If you look at the picture on the bottom right-hand corner of this slide, you see the carbon steel coupon sitting on a hot plate with a piece of PVC pipe sitting on top of it, sealed at the joint between the PVC and the carbon steel. and then there is a piece of tubing with a little straw at the end that enters into the PVC pipe. The liquid is dripped onto the surface of the coupon. The hot plate is operating at about 230 degrees Fahrenheit. So as the liquid drops onto the coupon, it boils off, leaving any contaminants or corrosive compounds behind. The dripping and evaporating cycle is repeated for 96 hours. Prior to subjecting the coupon to this test process, the weight or mass of the coupon is measured. At the completion of the 96-hour process, the coupon is measured again, and the difference between the initial and the final mass of the coupon is then used to calculate a mass loss corrosion rate, or MLCR, for each insulation material. So if we take a look at some of the results that have been developed for using this ASTM C1617 method for evaluating the impact the materials will have. This is some data that was developed by a third-party outside laboratory. And what it is representing is the mass loss corrosion rate ratio between the insulation material and the baseline corrosion rate for DI water. DI water, as many of you probably know, is considered to be pretty inert and not have a high level of any type of contaminants in it. So using that as a baseline gives you a good comparison for looking at the corrosion rate as a result of introducing anything that may have leached out of the insulation. If you look at the three bars on the left half of the chart, the orange, gray, and dark red bars representing the results for silica aerogel and water-resistant mineral wool products, you can see that they had a mass loss corrosion rate ratio between 2.5 and 3.5 times that of DI water, whereas the material represented by the blue bar in the middle of the graph, which is the Insul-Thin microporous thin blanket material, had a corrosion rate very similar to that of the DI water, and the Thermo 1200 calcium silicate and Sproul WR 1200 perlite products both had a mass loss corrosion rate ratio significantly less than that of the DI water. And as we'll demonstrate a little further in the discussion, that is a direct result of both of those products containing the XOX corrosion inhibitor. So you can see from this data that products containing the XOX corrosion inhibitor, that being the Thermo 1200 calcium silicate and the Sproul perlite, have a mass loss corrosion rate that's less than half of that of DI water, so excellent performance in helping to prevent and delay the opportunity for corrosion to occur, whereas the silica aerogel and water-resistant mineral wool products all had mass loss corrosion rate ratios significantly higher than that of the DI water, demonstrating that those products all did introduce additional compounds or chemicals into the system that could contribute to an accelerated rate of corrosion. Some additional analysis that was done at the conclusion of this test, looking at the residue that is left behind on the surface of the coupons after the test is concluded, demonstrates that the two products at the top of the chart, the calcium silicate and the perlite that both contained the XOX corrosion inhibitor, showed very little to no presence of iron on the surface, which would have been indicative of a corrosion condition. And both also showed a very high prevalence of silica and sodium ions on the surface. And again, that is the direct result of the corrosion protective features of the XOX corrosion inhibitor, and we'll talk about that a bit more in the following slides. The next material down on the chart, the hydrophobic microporous blanket, while it did not show a significant or a similarly high rate of silicon and sodium ions being left behind. It did still show a extremely low level or degree of iron behind. So again, clearly showing a very low corrosion rate. Whereas the last two products on the list, the water repellent mineral wool and the silica aerogel blankets, both showed very high percentages of iron on the surface of the coupon, indicating significant levels of corrosion and very low levels of silica or sodium ions. So again, showing very little protective compounds being present in the materials.
Now let's take a look at the longer-term testing that Scott discussed a little bit ago. So this test was developed by leading industry experts, and what it is meant to do is be a longer-term in duration. So this is a 6-month test. But what we're trying to do is basically take a pipe to failure in 6 months and then analyze the results. So we're trying to boil down what a pipe would see roughly in its lifetime, 20 to 30 years in a 6-month period. This test has been run twice, and the first test was run with the Insulthin HT product and silica aerogel. The second test was run with the perlite, the Sproul WR1200, the calcium silicate, and the silica aerogel blanket. So if we take a look at what we actually did with the test, we're going to focus on the pictures there in the top right of the screen there. So out of those two pictures, the one on the left is going to be an overhead shot of the testing vat. And what you're going to see there is you're going to see the actual pipe. It is insulated, and it's got the metal jacket on it. What you don't see is on the underneath side, there's a hole drilled in that jacket. The purpose of the hole is to allow moisture and water to infiltrate the system. Make sure that you're seeing on the upper right-hand part of the screen there, that's the picture of the actual testing vats full of liquid. So what did we do? We tried to simulate wet and dry conditions over this 6-month period, and we went from filling the vats to draining the vats at temperature and then at ambient. For 2 of the 6 months, the vats were filled with regular tap water, and for 4 of the 6 months, they were filled and drained with a 1,500 part per million chloride solution. If we take a look at the actual results here, this is going to be the results of the first test. And you can see there on the left the pictures of the pipes. The top pipe there is going to be your Insulthin HT, and the bottom pipe is going to be the silica aerogel pipe specimen. And again, we're going to go back to that pitting and crevice corrosion that we were talking about. And what we're looking at on that chart on the right is going to be the pitting depth. So you can see the maximum pitting depth on the Insulthin HT sample was less than of the silica aerogel specimen. We look at the test results of the second test that was run. Again, you have your perlite, your calcium silicate, and your silica aerogel, as represented on the pictures there on the left. The perlite's on the top, then the calcium silicate, then the silica aerogel. And that graph there on the right is showing us the same thing. We're focusing in again on that pitting and crevice corrosion, that pitting depth. And we can see that the maximum pitting depth in the perlite and the calcium silicate was a lot less than the silica aerogel specimen. So we've talked a lot about this pitting and crevice corrosion. But I like to look at pictures. To me, pictures say a lot. And so this is a magnification of the pipes that were used in test 1. So we look at that picture there on the left. This is going to be the Insulthin HT specimen. And what we're looking at is a cross-section picture of the test pipe. So what you're looking at, the black area at the top, that's going to be background noise behind the actual test sample. The white at the bottom of the picture there is going to be the actual pipe itself. The red line's pointing to that surface corrosion riding on the top of the pipe. The blue line is pointing to that actual localized pitting corrosion, so that pit that extends into the metal. And we can see on the Insulthin sample, it's relatively small. So we look at the sample on the right. This is going to be the silica aerogel specimen. Again, that white on the bottom is the actual pipe itself. The black at the top is going to be background noise. You can see the red line pointed to the surface corrosion. And then we can see that pit, and that pit extends further into the pipe specimen. Again, with this pitting corrosion, this is where you could actually have a failure with minimal overall thickness loss, wall thickness loss of the pipe. We want to better understand just how this impact of the insulation chemistry really pertains. So what's going on here? So we're going to take a look at the insulation chemistry of some of the products. The first thing we're going to do is look at the XOX corrosion inhibitor compared to just with something that's hydrophobic. So if we look at the attributes, first off is the XOX corrosion inhibitor and most products that are hydrophobic, that is integral to the product. The XOX product will not burn off in applications that go above 600 degrees, where the hydrophobic product will burn off at elevated temperatures over 600 degrees. While the XOX does not fight water ingress, the hydrophobic product does, but the XOX is present for the life of the product. So it's going to be there from installation until the product is removed, while the product that is hydrophobic may or may not. So the life of the hydrophobic agent is going to be dependent on the temperature that the product sees over its lifetime and the time at that temperature.
So let's take a look at what the XOX corrosion inhibitor is doing and how it can help contribute to delaying or significantly protecting against the opportunity for corrosion to occur. The XOX corrosion inhibitor is basically an alkaline compound. It's a combination of calcium, sodium, magnesium, aluminum, and potassium silicates. These alkaline components introduce a high pH or alkaline nature to the insulation system. So if for some reason you do get the introduction of corrosive ions into the system, typically from the outside environment, so it could be acid rain, or if this is a facility that produces a caustic compound and therefore that compound is creating a caustic atmosphere in the facility, if you get the introduction of those corrosive ions into the insulation system, they are actually going to combine and react with the alkaline ions from the corrosion inhibitor, and those acidic or corrosive ions will get neutralized and the pH will be brought back up to 7 or above, therefore hopefully eliminating the opportunity for that corrosive environment to be present in the insulation system and definitely at the surface of the pipe. So that's the first stage of protection, is by buffering the introduction of any possible acidic elements to the insulation system. The second level of protection that the XOX corrosion inhibitor provides is by creating a protective coating on the surface of the pipe or equipment that has been insulated. So if you do get water penetrating the insulation system, as it penetrates the insulation material, it's going to dissolve those molecules of the different silicate ions that are in it, and it's going to carry those silicate ions to the surface of the pipe or vessel. Those ions are going to then react with the surface of the metal and form a protective silica gel or coating. It's not a coating that you can see. It is molecular in thickness, but it is a protective coating that will be there for the rest of the life cycle of that system, and it is going to provide that protective layer on the surface of the metal. So if you do then get future introduction of water into the system, or the future introduction of any acidic or corrosive compounds into the system, that protective layer will shield the pipe from the opportunity for it to corrode the surface. You can see that insulation chemistry is very, very important to the opportunity for protecting your system against corrosion under insulation. Much stronger influence than that of the insulation material just being hydrophobic or water resistant. And that is primarily through the ability of the material to provide a protective layer on the surface of the metal, and therefore protect it against the opportunity of corrosion occurring. And that protective layer or surface layer will be made up of known corrosive inhibiting chemistries, basically those sodium and silicate ions or other chemistries that are part of the formulation of that compound. So taking a quick overview of everything that we have reviewed with you today, as RT very eloquently pointed out, your first line of defense is a well-sealed and properly installed jacketing system with careful attention being paid to making sure that the appropriate materials are selected based on the operating conditions and environmental conditions of the facility. And while hydrophobic and water-resistant insulation materials can help and do have their place, it's important to keep in mind that depending on the operating conditions of the facility, that protection may or may not be there for the life of the installation and the insulation material. So you can't count on them to be a cure-all for helping to delay or prevent corrosion under insulation. And as we've reviewed with you, industry-recognized test methods have demonstrated clearly that insulation chemistry has a much more significant impact on the corrosive potential than just material being water-resistant or hydrophobic. And with that, we'll turn it back over to Kim. We'll do a quick overview for you of some additional resources that are available from Johns Manville.
Excellent. Thank you so much, Scott. So before we dive into questions, and we've gotten a lot of them, I did want to talk about some additional resources that we have. So if you're looking for more information about this topic or other educational resources relating to industrial insulation, I'd encourage you to visit the source. And this is an online portal that we have where we house our latest blogs, our recorded webinars, our online tools like the Part Product Selector tool or the JM NEMA 3E Plus tool, ebooks, and other technical documents. So this is a great resource for anybody looking for more information, and this is where we will post the recorded version of the webinar once we post it live. And we'll send you a link when that is live on the website. Now, in addition to the source, we also have a resource library dedicated specifically to information on CUI. And so this is where you can find all of our webinars, including the webinar that really details that long-term corrosion testing that Chad talked about. We have CUI-related ebooks. We have a list of all of our products that we have that are designed to help you combat CUI. So those are all, that's another additional resource that's great, and that is also on our website. And we'll also be attending the NACE 2020 Corrosion Expo March 15th through the 19th in Houston next month. We're going to have 3 presentations there. 2 are under the research in progress category, and these are where our engineers who did the research are going to be discussing. The first one will be the mechanism of the XOX Corrosion Inhibitor and its longevity after repeated wet-dry cycling. And then the second one is, it was a study on how to dry an insulation system after a major flooding event. And so it's basically about designing systems that can recover quickly after you've had a massive amount of water ingress. And then Scott Sinclair, who presented here today, will also be giving a presentation on the myths of insulation treatments in CUI, what works and what doesn't. So he'll be diving into how insulation and maybe some of the myths that have developed around insulation forming CUI. So you can also stop by our booth and see each of these products that we've talked about today and our industrial insulation options for yourself. We'll have a swath of our hydrophobic and water repellent products there. You can see how they are, see how they work, and see how they operate with water. So in addition to that, we'll be hosting our next Engineering Advisory Council on September 20th, or in September 2020. Our Engineering Advisory Councils are an opportunity for our industrial engineers to speak to JM, basically, as an insulation manufacturer, and you can tell us about your pain points, trends you see occurring throughout the industry, and how JM can actually help make your life easier. For these events, JM does cover the expenses for travel, room, and entertainment, and we also offer a 4-hour completion certificate for attending, like the one you'll receive for this webinar today. So if you're interested in attending that, you can let us know in the follow-up survey. There's a question in there. Just mark yes. We'll follow up with you as we get closer to the event. And as for certificates of completion, anybody who attended today will receive one in their email by Friday, and this can be submitted for professional development hours. It is up to your governing body whether or not they choose to accept it, but you can submit it. So with that, let's take it to some questions. We had a lot of great questions submitted right out of the gates, and this was with the registration, so we're going to start with those, and then we'll dive into the ones that we got from the webinar. So the very first one, Scott, I will direct to you, and that is, how long does XOX last at elevated temperatures at 350 degrees and above, both in constant operations and cyclical conditions?
As we mentioned during the presentation when we were talking about XOX Corrosion Inhibitor, it is integral to the chemistry of the insulation material. So it is a protection that is there for the life of the material and the life of the installation. And once it has reacted and provided that protective layer on the surface of the metal, that also will be there for the life of the installation.
Excellent, thank you. The next question that we have is, has there been any testing done that was performed on our XOX corrosion inhibitor at these elevated temperatures to prove your answer, Scott?
Well, the data that Chad reviewed with you does show those were both done at elevated temperatures, 600 and 900 degrees Fahrenheit, showing that the performance is there even at elevated temperatures, and the compounds that make up the corrosion inhibitor are designed to operate over the entire operating temperature spectrum or range of both the calcium silicate and perlite products, which is up to 1200 degrees.
Excellent, thank you. The next question we have is, how effective is silica aerogel both for hot and cold temperatures at mitigating CUI? And Chad, I'll go ahead and send that one over to you.
Well, if we look at the long-term testing that we talked about today, and we look at the Insulthin HT, the calcium silicate, and the perlite in comparison to silica aerogel, while silica aerogel, I would say, also based on C1617, will perform probably on par with a mineral wool. What we see with these tests and then the long-term test is that the calcium silicate, the perlite, with the XOX corrosion inhibitor performs significantly better than the aspen aerogel when it comes to CUI.
Excellent, thank you. So can corrosion, corrosion can be minimized, but is there a way you can precisely predict when to replace a part or affected part or item?
I wish we could answer that one for you. If we could, we probably wouldn't need to be working anymore, but to get the answer to that question, I think you would need to reach out to a metallurgist and a corrosion engineer who would be better positioned to be able to tell you, based on some mass loss corrosion rate information, at what point you would be at risk for potential failure and therefore need to start repairing or replacing piping and equipment.
Thanks, Scott. So our next question is there any study material that can be shared on CUI? I'm going to go ahead and answer this one. Yes, you can get it on our CUI resources page. If you go to the industrial page of the Johns Manville website, you'll see a menu on the left-hand side, and at the top of that menu is a link to the CUI resources page. This is where you can find all of our material that we have on CUI, and this webinar itself will be posted up there when it's recorded and ready for you to watch on demand. The next question we have is for you, RT, and that is there a way one can detect corrosion under insulation without removing or losing the cladding?
I think it's pretty simple. As far as getting firsthand, I would say the cladding does need to be removed to inspect the insulation material itself.
All right, thank you. The next question we have is, Scott, I'll go ahead and throw this one to you. Do you have a smart insulation that can detect a degradation, a wall degradation, while it's on the pipe insulation, on the pipe itself?
I'm not aware of how you would do that, to be honest with you. So I guess the direct answer is no, there isn't an insulation material that can detect how much corrosion is occurring beneath it.
Interesting concept, though.
That would be great.
And this is Jim Young. There are supposed to be a number of relatively new radiographic methods that can detect corrosion to the pipe or tank underneath the insulation using X-ray or other type of techniques like that. None of these are JM products, so I would suggest that the question asker search for radiographic corrosion detection. Just a Google search, and they could probably find some things.
Excellent, thank you, Jim. And for those of you who are on the phone and wondering who that was Jim Young. He's one of our technical guys, and we had him on the call for some of the more technical questions, like this next question I have here for you, Jim. So that is Could we use the same corrosion protection under jackets and PU insulation in a combined cycle plant?
It's possible. I think any type of corrosion inhibitor that could be used on the pipe or tank could be used under the PU or PIR insulation. It will not hurt the insulation. Do remember that PU or PIR insulation has a maximum upper surface temperature of 300 degrees F. So that might be a limitation that might prevent use of that particular insulation. But there are no corrosion inhibiting materials that would damage the PU or PIR insulation itself.
All right, thank you, Jim. So the next question is, if I have any doubts or questions about this topic that was presented today, how can I get clarification? If you'd like to seek out clarification for yourself, you can certainly do it online. Like I said, a lot of this information is already posted online via ebooks or technical bulletins. You can also reach out to a regional technical manager like Scott Sinclair on the call today. And you can do that through the Contact Us page on our website. So Scott, Jim, those would be excellent resources for anybody who has any questions after today's presentation. Chad, I'm going to give this next one to you, and that is you can defer here, but how do I prepare a proper inspection plan for a CUI in a refinery?
Wow, I think I would probably defer that to either Jim or Scott. I think there's a bunch of different ways we could go about it, but Jim, Scott, do you guys have any thoughts on the matter?
You know, I don't want to be, this is Jim Young, I don't want to be flippant here, but it's really largely outside the purview of JM to specify that. It's going to depend on so many factors, the temperatures, the materials used, both pipe and insulation, the maintenance, the inspection. It's a case of, you know, your mileage may vary. And it's really up to, I think, the site leadership to determine the proper frequency and types of corrosion detection or corrosion inspection, rather, methods that they employ.
Yeah, this is Scott Sinclair. I agree completely, Jim. That's really not something that Johns Manville can specify what type of an inspection program you should do. A big piece of any inspection plan is going to be a detailed risk assessment from the viewpoint of cost impact of not catching a problem up front, but also risk assessment from the viewpoint of the expense of doing inspection and looking at the risk of different areas, as Jim was highlighting, in terms of the operating conditions, the environmental conditions. Are there certain areas of pipe that might be exposed to wash from an evaporative cooling system and therefore at high risk, or chemical exposure and therefore at high risk? So there are so many variables. It really is something very specific to every facility.
Thank you so much, Scott, and for the rest of you for weighing in on that one. Jim, I'm going to send this next one to you, and I suspect it would have to refer to a cryogenic application, but that is, how does heavy ice affect insulation and piping on vessels?
Well, heavy ice, I think you could think of it in two ways. The simpler way is freezing rain or something like that, or snow that is condensed and frozen. So if the source of the ice is exterior and it's just hanging on the pipe and the insulation, the issue is going to be solely one of weight on the supporting systems and probably to a lesser extent, much lesser extent, crushing of the insulation itself. I mean, you'd have to have an incredible amount of ice to really get enough weight per square inch to damage the insulation. So I think it might be more a case of, you know, trees tipping over from the combined mass sort of a issue. Whereas when you got a mile of pipe, if it's all has ice on it, you've got a lot of extra weight there. So I think that would be, even though it's a small weight per square inch, so it's not going to damage the insulation system, I think the support issue is probably the more of a concern. So I think I would approach that more from a concern of, is your overall structural system that's supporting the pipe and pipe insulation strong enough? The second possibility of that is if it's a cold pipe and water has gotten inside the insulation system and formed ice inside the insulation, that's a completely different animal. And in that case, your system is basically trash. You know, just to cut to the chase, if you've got so much water inside your cold pipe insulation system that it's forming ice, that's irreparably damaged, and you kind of have to start from scratch, start over with your insulation system.
Great, thank you, Jim. I do realize we're coming right up to the hour. We have over 50 questions that have been submitted, and we would like to address as many of them as we can. So we will probably continue on until about the 15 after or even 20 after the hour. So if you want to sit tight with us and listen to questions, great. If not, we will answer as many as we can until you guys have to take off. So the next question is for Chad, and that is, how is calcium silicate better than perlite?
Well, I think kind of an interesting question. I think it also depends on a couple things. Depends on your application, and it probably also depends on where you're at in the country. Up here in the upper Midwest, I would recommend calcium silicate for a lot of the applications up here. One, due to the way it transits when we ship it to the job site. If your application's down more towards the Gulf area, you're near a large body of water, I would recommend perlite, because perlite is fully hydrophobic. So really, it's going to be dependent on the application itself as to which product you're going to choose.
Thank you. The next question is for you, Jim, and that is it possible to find CUI in stainless steel pipes on cryogenic services?
It's possible, but very unlikely, unless the pipe is undergoing a cyclic temperature system. The stress corrosion cracking of austenitic stainless steel is a temperature-related phenomenon. It only occurs between approximately 140 degrees F and approximately 250 degrees F. We can argue a little bit around those numbers, but certainly nothing much below 100 degrees F. So if it was a cryogenic pipe, the chemical reaction of stress corrosion cracking would simply not occur. If, on the other hand, it is cycling in temperature from cryogenic up to room temperature, that's one of the harshest environments for CUI. When it's cold, it tends to draw moisture in. When it warms up, the chemical reaction of corrosion is exacerbated. The best way to prevent that from happening is through the proper design and installation of a very, very water-resistant insulation system. Closed cell insulations, high-quality vapor retarders, proper jacketing, etc. The details of that, of how to accomplish all that, are of course way outside the scope or time we have allotted here. But the inquirer could be happy to contact JM, and we could give them lots more information on that.
All right, and that wraps up our final question. Thank you, everybody, for joining us today. A live recording of the webinar will be posted online within a week. So we look forward to hearing from you in the future, and we hope you have a great week. Take care.